Okay, so C is the heart and soul of this whole thing. We like trig functions so we can model things with them. So you have to find four things, right? You got to somehow figure out the amplitude. How high up above equilibrium does this go and how far down? That's the amplitude. It's A. It's half the difference between maximum and minimum. You need to find the period, right? How long does it take to make one full oscillation? That'll help us find the B value, right, to put in our equation. And we can use this. 2 pi over B is the period. You need to find the vertical shift. Usually on these equations, the equilibrium point is at 0. So you got to figure out where the equilibrium point is, up or down, above or below that, and just add or subtract to the end, and that's your D value. And then I think the hardest part is this horizontal shift, moving it back and forth to get it lined up right, and we'll talk about that too. Okay, so let's try one of those. This one's from your text, and you can see it in there too, and then I'll show you one after this that's not part of your text. But they just gave you this data. They said, hey, January, February, March, blah, blah, blah. We're talking about month versus temperature. Right? And they didn't even give these numbers. They just gave them names. January, February, March, blah, blah, blah. And plotted these points in degrees Celsius, and away you go. And they said, okay, well, now give me a equation with this being temperature and x being the month or number, and plug in A, B, C, and D to really match that up. Okay? Well, a couple of things that we can see right away is that this isn't oscillating at the normal 0 mark, right? Because most sine cosine curves do this sort of thing, right? So right away we know that we're going to have to figure out where the equilibrium mark is for this curve and drag it up to there. So let's look at that. Let's find the maxima and minima. So it looks like 27, 28, 29 is the maxima. It's up here, right? And the minima are down here maybe at 15, 16. So here's 16. Yeah? So we have to find the average between those. Yeah? Great. All right. And so it seems like the average is around 21. Yeah? I think if you find the maxima, minima, and then average them, the average, I guess, is going to be, what, 11 or 12, cut it in half, so the equilibrium point is going to be 21, so like right in the middle is going to be around 21. Now, that's arguable, but we're going to go for 21 as sort of the average point, okay? So let's look at it like this. The amplitude A, I think they're going to use 6.5. So 12, 13 is the distance between here and here, right? So this, if you subtract the highest and lowest, that's going to be 13. That means this is 13 units between here and here. Yeah? Cut it in half, so 6.5. So that's the distance between here and here, 6.5. Or that's the distance between here and here, also 6.5. Cool? So that means that our A value is 6.5. Great. All right. And that makes sense. So if you go from 29 and you go down 6.5, or if you go from 15 up 6.5, you get to this equilibrium value, which is around 21. And I think they're calling it 21.5 in this case. So the vertical shift, this thing isn't oscillating around 0. It's oscillating around 21 or 21.5. So the D value, the amount that we have to move it up, is 21.5. Okay, we're just harvesting that right from the data. So those should be fairly easy to find. This is the next toughest one, and then we'll find C. So the period helps us find B. Let's look at how long it takes this thing to oscillate. Well, it goes from maximum to maximum in, a year. So 12 months, right? From here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it oscillates in 12 months, right? So the the 2 pi over b, we want to find this b value and we don't know it. So 2 pi over b, and I know the period is 12 months. So then we multiply both sides by b, divide both sides by 12, and you end up getting b is 2 pi over 12, otherwise known as pi sixths. Oh, 2 pi over 12 or pi sixths. So pi sixth is going to be our b value, right? We just solved this guy. Sorry about this mess. Okay, so we got our b value. So this thing is going to look like this, right? The 6.5 is the amplitude. The 21.5 is how much we've dragged this whole thing up from equilibrium. And the pi 6 is our b value that we got from looking at how long it takes to complete one period and finding b using this. Okay, great. So so now we got to find the c value because well, here's why. If you take this and you plug it in, you're gonna get this. If we graph this, you get this red line, and it's not where we want it to be, right? It's a sine curve, so it starts at 0, and then it comes up in maximum to a maximum, comes back down to equilibrium, dives down, and then returns to 0 around here in January. Mine's a little bit off because I was hand drawing it, but it should go through one cycle and end up back to 0 here, right? So we've got to slide it, and we can slide it either this way and lock it in, or see my little green dot is my initial point, or slide it this way and lock it in. Now I'm off a little bit because I did a pretty junky hand drawing on this with my computer mouse. So let's do this. We were here. Let's try to move it here, like that. Okay, let's try to move it over just a little bit. So I want to take a point and just slide it. Yeah, so here's some original data that I'm going to look at. I know I just looked through my original data and I found that in October I had a point on the equilibrium. So here's September, October. This point, point A, is right on the equilibrium. So one thing we could do is take this point that's supposed to be on the equilibrium, this green point, right? I know that starts on the equilibrium, and just grab that and drag it over to point A. And then we lock in, and we've got this all synced up. So how do we get it to do that? How do we drag our graph over? Well, let's see. I'm dragging it over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units. Right? I'm grabbing it from here, dragging it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units to the right. And you don't even have to count. I know it's 10 units away from where I started. So my C value, what I'm going to put in here, is going to be 10. Cool? So this really should look like this minus 10. So there's one equation for it, right? Another equation for it, I mean, it's hard because there's so many equations that you can write for this. So another way you could do this is think about this. Let's take this point. This is my maximum. I know I have a maximum here at January. And I know that this maximum will happen 1, 2, 3, well, let's see, the whole thing's 12 units. So this will happen 1, 2, 3, 4. This will happen a fourth of the way. So this is 3 units away from 0. So I could drag it 1, 2, 3 units back, right? So I could grab this and drag it 1, 2, 3, and then hopefully it would link up again. So another way you could think about it is drag it 3 units to the left, and so we could just, instead of that, we could just say plus 3, right, instead of minus 10, because we're just dragging it the other way. So the good news is there's a ton of ways to write it. The bad news is there's a ton of ways to write it. Sometimes they'll give you some direction. Cool? All right, so we can also do the same thing with cosine. I'm going to show you that real briefly, show you one more example, and then you're on your own. There's homework here. You can pause it now and start it up if you want. Just write it down, or you can check out cosine with me and one more example. Those are the hardest parts, so stick with me if you got it. All right, cosine is sometimes easier to model because it starts at the maximum or minimum. So let me show you this guy again. If we change this to cosine, I know that cosine starts here. Cosine is talking about how far over this point is on the unit circle. Yeah? So we always start at the farthest distance out, here at 1. And then it drops off, and once you get to pi halves, it's not any over. It's just straight up. So now it's at 0. And then it goes backwards to -1. And then it goes down, and as you go back here, it comes back to 0. So it goes up to 1, 0, -1, 0. Blah, 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 blah. So it's the same sort of thing. It's just skewed over one side. And so sometimes it's easier to use this when your system is starting at a maximum or starting at a minimum. Let me give you an example. Well, so if you've ever been on a Ferris wheel, like Navy Pier in Chicago, you've seen that this just like is an oscillating system based on height. So the car goes up, the car goes back down, etc., etc. So they said it takes 7 minutes to go up and around all the way back and back like that. That takes 7 minutes. On a Ferris wheel, the maximum height it gets to is 150, and the minimum height it gets to is 10, right? It can't be at 0 or you're like smashing into the ground and you have a fiery wreck, and that's bad. So we want to model this with cosine. You can model it with sine. Okay, so let's give it a shot with cosine though. I know a couple of things. I know that this starts at 10. Right, so here's 50, this must be 10. I know its maximum height is 150. Cool? So the distance between there is 140, and halfway between that is 140, half of that is 70. So from here, it's got to be 70 up. So 10, 20, 30, 40, 50, 60, 70. So I know my minimum is at 10. I know my max is here at 150. So this equilibrium point got to be 80, right? So I just said, all right, 150 minus 10, and that gave me 140, and then I divided it by 2, and that gave me my amplitude of 70, right? That's my amplitude, and then this is the minimum, and this distance is 70, so then I added my minimum to it and got 80 for the location of the equilibrium. Okay? So that's just kind of like nuts and bolts stuff. I hope that you don't memorize formulae for that. You're just analyzing the situation. Okay, I also know this. I'm starting here at 0. At time 0, I'm at 10 feet up. You have to get on a ladder to get in this thing. And it says 7 minutes later, I've made one full rotation. So I've gone all the way to the top and all the way back down here to 10, right? I'm assuming halfway in the middle, I'm at my maximum. And then I'm assuming halfway between there and there, I'm at my minimum and at equilibrium and at equilibrium, which is the axial level, right? Let's get that better. That's not much better, but this is 80, right? So I go up, I hit 80 feet, which is my equilibrium. I max out, so that was here. I max out halfway to 7 minutes, which is 3.5 minutes. I come back down to this equilibrium point here, and then I bottom out again here, right? Okay. So, great, we got these sort of points going on, okay? And so I know a couple of things. I know this is going to look like, let's try this with cosine. I know that the amplitude is 70, so this is going to be, all right, well, 70 cosine of b times x and some horizontal shift c. And then I'm moving it up. And I know my move up is always the location of this equilibrium point. So that is, it's not, this thing isn't oscillating around 0, it's oscillating around 80. So I have to take that average that was here at 0 and move it up to 80. So all we're doing is adding 80 to this. Cool? So let's find B, right? B, I know, is 2 pi over B is the period. And the period for this thing, well, goes up, goes down. That up, down takes 7 minutes. So this period is 7 minutes. So we're just going to rearrange this, multiply by B, divide by 7, and you end up with B is 2 pi over 7, right? Don't give me a decimal. Leave it, man. Leave it. Resist the temptation to grab your calculator. Oops. I get so excited. Sometimes I just start drawing all over. Okay? There's your B. Plug it in. Like that. Okay? So, all we're looking for now is this blessed C. Great. So let's find it. Here's a better drawing. Cosine starts at its maximum, right? It's all the way out. It's all the way over. The x is 1, right? And then it dives down to 0, and then negative, and back to 0, and then back to its maximum. That's what cosine does. Well, this sort of thing, let's see, this guy doesn't really do that. It starts at its minimum. So one thing that we can do, here, let me steal this back. One thing we can do is slide it, right? So we could add something to C and move it so the minimum is here where we want it to be, right? So one thing we could do, let's see, this is 7. I know we want it to start at 3, so we want it to start at 0, so we could slide it one way, like this was at 3.5, and if we slide it 3.5, it'll start at 0 where we want. So we could add 3.5 to the C, or we could subtract 3.5 as the C, right? Either one of those would be fine. Or we could do nothing with it, with the C, and just flip this over. Shunk. And so it's starting at its minimum instead of its maximum. And all you have to do is go bink, and forget about the C. Right? So it doesn't matter which one you do. Any of those will be just fine. Right? So this works. So here's one equation. Great. Or you can keep your, if you don't like the negative, we can add, what was it, 3.5. So plus 3.5. We can add 3.5 or subtract 3.5 just to shift it over one way or the other way by 3.5 units, right? And it doesn't matter which one you do. Pick the one that's easiest for you, and maybe the one that is the most efficient, because time is of the essence, right? So either one of these are great. There's 2 equations. Cool? Doesn't matter which one. Or you can shift it more. I mean, you could shift it a long way, like that. Yeah, it doesn't matter. All right. So I hope that helped. Sorry you guys were gone again. I know that's a pain, but we're doing the best we can. All right. Here's a little practice for you, and good luck with yourself.